So we're going to look at the Lewis theory of bonding 4.1, and our goal is that you can draw Lewis dot diagrams for ionic and covalent compounds. So let's take a look at the octet rule. The octet rule states that atoms are only stable or happy when they have either 8 or 0 valence electrons. Now, of course, to do this 8 or 0 valence electrons, there's going to be some sharing, some gaining, or some losing. So the octet rule will help us in making predictions about the shape of molecules, and there are a few exceptions we're going to encounter. So molecules with an odd number of electrons may not follow the octet. Molecules that have less than an octet, and molecules than an atom that has more than an octet. So meaning more, just you've got more than 8 valence electrons surrounding some of these things. So we're going to counter that. Now I want to talk a little bit about the Lewis theory of bonding here. It says atoms and ions are only stable if they have a full shell of valence electrons. Electrons are most stable when they are paired. That's what we're after, pairs. Atoms form chemical bonds to achieve a full octet of electrons. A full valence shell of electrons may be achieved by exchanging electrons between metals and nonmetals, and this would be the gaining and losing thing that I was just mentioning. A full valence shell of electrons may be achieved by the sharing of electrons. So by the way, this is going to be the ionic thing when you gain and lose, and sharing is going to be covalent. And we'll be learning more about that in a second here. And lastly, the sharing of electrons results in covalent bonds. Yeah, just what he said. Ionic bonding. So ionic compounds, a compound that contains an ionic bond. So ionic bonds are created when electrons are lost from a metal and gained by a non-metal. So they make a nice partnership. So they're made of metals and non-metals, or another way to say it is they're made of cations, which are positive, which would be the metals, and anions, which are negative, which would be the non-metals. So here's an example. This would be a sodium reacting with chlorine gas. And so what's happening here is our chlorine is a chlorine gas. The bond is breaking between these two things. And we've got the one electron from sodium going in to fill that chlorine's octet, and the exact same thing is going on there. So in essence, you're making 2 molecules of NaCl. So let's look at some ionic bonding here. Let's do it exactly with the sodium and chlorine here. So we've got sodium in group 1, it has 1 valence electron, and we've got chlorine in group 7. And what we're going to do is we're going to be able to take that valence electron from sodium and put it with chlorine. So in essence, what we've done is we have emptied the outer shell. It has a stable plus charge. We don't show that though normally. And then we've got chlorine that's gained an electron. It's now got a full valence shell, 8 valence electrons. It has a negative charge. We don't really show that either. But what this does show is that every time you put sodium and chlorine together, it's a 1-to-1 ratio, and you get sodium chloride, 1 of each atom. Let's turn it up a notch here. Let's go with magnesium. That is in group 2, so it has 2 valence electrons, and put that with fluorine that has 7. Now, this starts off nice. We can make that fluorine happy, but the problem is we still have a magnesium that has 1 valence electron. So the move would be to add another fluorine so that we can put that valence electron in that spot. And there you go, looks like that. So what we've discovered when you put those two together is that you get 1 magnesium and 2 fluorines always, and that would be your magnesium fluoride. Now, this method can get a little crazy, if you will. What happens when you put aluminum and sulfur together? Well, it starts off nice because you can take that electron and put it there, and that electron and put it there, and you can make sulfur happy, but aluminum still has an extra one, so we add in a sulfur, and we can put that one there. But then we have an unbonded sulfur here, so we'll add in another aluminum, and then that one can go there, and then we can put another sulfur there, and then finally we can put this to rest. And I'm just going to draw it like that. I'm not even going to draw the valence electrons. It's starting to be crazy. But we've discovered that we've got 2 aluminums and 3 sulfurs. So don't forget, this is really coming from the crossover method that you learned back in the day. That's aluminum sulfide. Now, covalent bonding is different. So these are compounds that are made of nonmetals. Electrons are being shared between the 2 atoms, and that is allowing all the shells to fill up. So the sharing allows shells to fill. So hydrogen is probably our simplest one. Now remember, it's just got 2 electrons to make it nice and stable. That's what we're after here. So we can put 2 hydrogens together, and there we go. And we've got our shared pair of electrons. And what I'm going to do with covalent compounds is I'm going to circle them. So this hydrogen here has access to both, and this hydrogen here has access to both of those ions, and so, or atoms, I should say, electrons, I should say. So we've discovered that they make a single bond with hydrogen. Well, let's turn this up a notch here with fluorine. What's going to happen with fluorine? Well, they're each in group 7, and so you can count my electrons. It's got 9 electrons, 7 in the outer shell. That would be our valence shell. And what we're going to do is we're going to add them together, and we're going to have that overlap. And if you count up the electrons in the outermost shell now, you should have 8 for this one. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. It's sharing those, and then you count the other one. 1, 2, 3, 4, 5, 6, 7, 8. So we've discovered that fluorine gas is a singly bonded molecule. Let's go to oxygen gas. So oxygen's in group 6. It has 6 valence electrons, and O2 is 2 oxygens. So what's happening with this one is we're actually ending with a double bond. I'm going to circle this right here. Each of those are sharing. So this oxygen has 1, 2, 3, 4, 5, 6, 7, 8, and then the one beside it 1, 2, 3, 4, 5, 6, 7, 8. So by sharing, we've discovered that we form a double bond between oxygen. Nitrogen's in group 5. It has 5 valence electrons. So what will work nicely here is it needs to share 3. That sounds like a triple bond to me. And that's what's going to happen. I'll circle my pairs. So each nitrogen should have 1, 2, and then 6 here. And the same thing here, this 1, 2, and that has 6. So both are able to fill its outer shell and fill the octet. And we discover we have a triple bond there. Water, H2O. So hydrogens with 1 valence electron and oxygens with 6. You'll see that these are a nice pair. I'm going to rotate the oxygen a little bit, put my hydrogens there, circle my bonds. Oxygen is able to get the 8 valence electrons it needs. Hydrogen is able to share and get the 2 that it needs, both of them there. And again, remember, hydrogen's nice and simple. It only needs 2. And we get our shape of water. Now, something weird's happening here. Water is bending a little bit. What's going on is we're discovering, which is going to be a future lesson about how to draw these accurately. You might have just drawn this in the past, just like straight across like this. It's not actually true. Water bends like this, hence our dipole. We're going to discover this soon. Methane, CH4, there's carbon, and those hydrogens go nicely there. We get sharing, the oxygens fill up, the carbons have 8, all is good. And again, you think your molecule might look a little like this. It actually, if you even grabbed a molecule kit and created this one, it would look like this. We got 1 up top and we have 3 down low. It's almost like a little pyramid if you kind of fill in the spaces here. It makes a little pyramid. So we're going to have to look more at that shape in the future too. Ethene. Now we know carbon is in group 4. It's got 4 electrons around it, and problem is this isn't going to really work out so nicely. We're going to have to move this around. We're going to have to form some double bonds. So that's going to be our first move, is to have a double bond between these two. And then if you'll notice that we're able to put our hydrogens very nicely together. So we got a double bond in red there, and we've got some yellow single bonds there. And again, when you put your shape together, it sort of bends a little bit. More things we're going to discover in the future. Ethene, C2H2. We've reduced the hydrogens, so we must be talking about a triple bond here. And you see that one goes together nicely. If you have a molecule kit and you can make these, that makes it much more simpler. I doubt you do. So it's really about filling up. Carbon should have 8 valence electrons on each of these now because of the sharing, and the hydrogens end up sharing too, so they are good. And your shape is actually straight across. That might be what you thought would happen, and it is in fact what happens. So let's work through an example now. We're going to look at SO3. There is no charge on this. So rule 1, which atoms are bonded? Well, we're going to go with S in the middle. It's the first one there, so we're going to put that in the middle. We're going to count all the valence electrons here. So S is in group 6, so it has 6. Oxygen also in group 6, but there are 3 of them, and so that makes 18. And 6 plus 18 gives us 24 to draw in total here. So that's what we're going to do. And let's do steps kind of 2 and 3 together. So we're going to place 2 electrons in a bond, and we're going to complete the octets of atoms attached to the central atom by adding electrons in pairs. So we're going to start with sulfur, and we'll use some dots here. And like I said, we're going to put some dots. We'll put all of these in pairs, and that's done. We're going to take our oxygens, and they're going to do the same thing. So here's more pairs around here. There's another oxygen, more pairs. Sorry, my X's aren't that great. And there we go. And we've now completed our 24 electrons. So our 24 valence electrons have been done. So place any remaining electrons in the central pair. We don't have that in this example. In step 6, if the central atom does not have an octet, which it doesn't, sulfur only has 6 going on here, we need to form some double or triple bonds. So what's probably the easiest thing to do is to say take 2 electrons, move them up here, and then we're going to have our double bonds forming. So this will look a little something like this. You got your sulfur, and it's got its 6 valence electrons. Then you've got your oxygen here, and there come my terrible X's. And it's in group 6, so it has 6. This oxygen, same deal. And then with this oxygen here, we shall put a couple there. And then lastly, because it's covalent and it's nonmetals, we'll circle those bonds. So it should look a little something like this in the end. You get a couple single bonds, and then we get our double bond between that oxygen and that sulfur. And really, it didn't necessarily even need to be this oxygen. It could have been any of the 3 oxygens because they're all sort of behaving the same way. So we do have some exceptions to this, which can cause some problems. So the octet rule works well for representative metals, groups 1 and 2, and the nonmetals, but not for the transitions. So all those things in the middle with all those D shells we've been learning about. And it has everything to do with those D and F suborbitals. So this is because the D and F have suborbitals. For example, tin forms 2 ions. It can be +2 and it can be +3. And so you look at our neutral tin molecule here. It's there it is. And so when we have +2, what's happened is we have wiped out the 5p. Those 2 electrons are gone. That leaves us to that example. And when we go down to the 4, what's happened is we've wiped out the s's. So that's how those ions are forming. So neither of these configurations are noble gas configurations, though. Close enough. So expanded octet. So some compounds contain more than 8 valence electrons around an atom. Elements in the 3rd or higher periods have room in the valence shell for more than 8 electrons. Right, so that 3rd period, that's now we're talking about the d orbitals, right? And so we've just got more room for than what we expected for 8 electrons. We can fit 10 or maybe even more in there. So here's an example, PCl5. This is phosphorus pentachloride. So you do your quick little math there. We've got 5 electrons for phosphorus and 7 for chlorine times 5 gives us 40. And when we go to draw it, it looks a little something like that. We end up with single bonds. And so if you count it out here, we actually have 10 electrons around this phosphorus. And again, it has everything to do with the fact that we have a d orbital involved now. And so you can have more than 8 electrons around it. They're spreading out in the d. You can also have the opposite of this, which would be an incomplete octet. So when the number of electrons surrounding the central atom is a stable molecule with fewer than 8 electrons. So common for elements in the 3rd group. An example would be BF3. Now what does the 3rd group have? Well, it's got some p orbitals. So there's our BF3, boron trifluoride. You do your math, you get that value, and then you do your picture, and you notice that the fluorines are all stable, but the boron only ends up with 6. So the fluorines each have 8 valence electrons, but our boron only has 6. And if you dig a little deeper, boron has a p orbital. And how many electrons can we fit in the p orbital? We can have 6 there. So probably what's happened is there's been a bunch of pairs that have been created in that p orbital, if you can picture it.